Every single night, hundreds of massive commercial airliners pierce the pitch-black freezing void spanning the North Atlantic Ocean. More than 300,000 international passengers sleep soundly, completely unaware of the invisible stratospheric network operating around them. Public perception dictates that these late-night transatlantic operations are merely matters of scheduling convenience or corporate marketing ploys. However, the cold empirical data exposes a demanding mechanical reality dictated by planetary rotation and severe thermodynamic constraints. This maritime corridor remains the busiest airspace globally, yet lacks continuous active ground-based radar tracking for thousands of kilometers. Flight safety across this pitch, dark oceanic abyss is never guaranteed by the intervention of manual air traffic dispatchers. Instead, survival relies entirely on the mathematical precision of executing a pre-planned, rigid, multi-layered corridor route structure. Tonight, dozens of modern commercial aircraft align precisely inside narrow tactical corridors spanning 5,000 kilometers over freezing oceans. External ambient temperatures drop rapidly at these cruising altitudes, plunging down to an extreme -60 degrees Celsius tonight. Powerful high-altitude, stratospheric winds strike the clean, metallic fuselages, reaching intense velocities of 300 kilometers per hour. Any microscopic flight path deviation inside this volatile, freezing environment immediately threatens the survival of hundreds of human lives. Heavy commercial passenger airliners enter this specific high-altitude layer between 9 and 12 kilometers for maximum aerodynamic efficiency. This thin, rarefied air layer exhibits unique thermal physics where the kinetic behavior of cold air masses completely dominates. Massive jet streams act like high-speed, invisible rivers of air, cutting directly through the calm upper stratospheric boundary layer. An airliner stabilizes at its cruising altitude before entering a powerful, favorable upper atmospheric jet stream current. While internal airspeed indicators remain completely unchanged, the aircraft accelerates rapidly relative to the physical geography below. Conversely, westbound flights heading toward North America encounter immense headwind resistance, losing massive amounts of operational time. Under standard atmospheric conditions, a passenger jet maintains a stable cruising velocity of 850 kilometers per hour. But extreme tailwinds can dramatically accelerate ground displacement speeds exceeding 1,100 kilometers per hour effortlessly. This immense natural propulsion reduces transoceanic travel duration by up to 1 full hour and 30 minutes continuously. Exploiting this physical tail wave allows commercial operators to conserve multiple tons of precious liquid aviation kerosene fuel. High-speed operations occasionally force closely stacked commercial aircraft to approach each other faster than separation protocols permit safely. Oceanic traffic management systems intentionally slow down fast airliners to maintain strict safe spacing intervals inside dense currents. Jet stream tracks continuously shift and morph daily, forcing regional route planners to rebuild the entire transport network. Extreme clear air turbulence zones manifest invisibly along high-velocity thermal boundaries, requiring tactical changes in cruise altitudes. Specialized meteorologists meticulously analyze severe temperature drops and wind profiles to publish between 5 and 10 official tracks. Every dynamic oceanic track operates as a precise chain of geographical coordinates preloaded directly into flight management computers. Organized air traffic flows utilize highly formal, alphabetized identification schemes understood universally by flight crews and oceanic controllers. High-altitude operations force advanced commercial passenger airliners to navigate critical thermal boundaries along complex upper atmospheric layers. Massive metallic wing structures experience profound structural load stresses when encountering invisible shear vectors inside the stratosphere. Mechanical analog control components monitor rapid air density drops to prevent severe aerodynamic stall at extreme operational thresholds. Experienced flight crews must maintain flawless path precision as the airframe encounters highly unstable, clear air turbulence sectors. Precise thermodynamic calculations prove that high-velocity jet stream channels create immense friction against titanium engine cowlings. Automated systems continuously balance mechanical power margins while managing fuel consumption rates inside sub-zero transoceanic corridor domains. Total structural disintegration remains an implicit danger whenever advanced aerodynamic limits are exceeded over the black oceanic void. Removing active solar radiation at night completely stabilizes the ambient atmospheric columns and dampens unpredictable vertical convective thermal currents. This predictable environmental equilibrium allows precision calculations of ground speed and critical checkpoint arrival times across transoceanic routes. A highly specialized nocturnal synchronization window emerges, allowing dozens of loaded commercial transport airliners to group together safely. Dense traffic flows navigate adjacent cruising flight levels, simultaneously crossing the cold North Atlantic airspace without systemic intersection conflicts. Westbound flights from European hubs exit into daylight windows, encountering severe continuous headwinds that disrupt ideal mechanical efficiency metrics. These opposing aerodynamic forces distribute return flows across broader daytime schedules, preventing dense, synchronized convoy grouping over oceans. The rigid mechanical alignment of global flight parameters showcases how modern transport relies on the invisible atmospheric night architecture. Empirical flight data validation proves how specific atmospheric currents create record-breaking speed anomalies across the maritime corridor. During February 2020, a heavy commercial wide-body airliner entered an exceptionally dense, high-velocity stratospheric jet stream flow. The massive propulsion system maintained standard thrust levels, yet the ground displacement velocity accelerated to unprecedented heights effortlessly. This unique commercial operation completed the entire transoceanic journey in less than 5 hours due to massive atmospheric kinetic aid. For direct technical comparison, archival records reveal an absolute supersonic record established during the late 20th century era. The legendary needle-nosed aircraft bridged the ocean in under 3 hours by entering extreme upper atmospheric supersonic regimes completely. Modern commercial transport aviation purposefully abandons brute technological speed in favor of strategic synchronization with fluid dynamics parameters. Sudden, unexpected mechanical anomalies along structural interfaces disrupt linear flight path calculations during high-speed transoceanic night transit phases. Internal flight instrumentation needles vibrate violently as intense clear air turbulence exerts extreme aerodynamic stress upon pristine composite wings. Flight crews must perform rapid manual system adjustments when severe temperature gradients alter localized air density parameters unexpectedly. Ground coordinators frantically track physical paper logs as localized wind, shear velocity approaches 300 kilometers per hour. Extreme kinetic pressure spikes within advanced turbine propulsion systems demand immediate tactical altitude corrections over the Black Ocean. Structural integrity margins degrade rapidly when heavy atmospheric loads bend complex, unblemished titanium structures past normal design limitations. The hidden files inside our secret archives verify that structural degradation remains a constant implicit hazard during midnight navigation. A single minute of flight trajectory deviation immediately triggers cascading arrival delays across heavily interconnected commercial aviation hubs worldwide. Early aircraft landings dramatically compress ground gate turnaround schedules, accelerating subsequent maintenance deployments for trailing long-haul operations. Minimized parking durations, optimized parking apron distribution patterns, preventing systemic logistical gridlock inside major transatlantic arrival terminals. Conserving multiple tons of unburned liquid aviation kerosene directly affects regional energy supply storage allocations for subsequent long-range networks. The structural optimization metrics analyzed inside our secret archives expose how tightly synchronized arrivals balance global maritime transport economics. Disrupted spacing intervals force global air traffic flow control systems to implement ground delay holds thousands kilometers away recursively. This intricate domino effect underscores why individual aerodynamic flight parameters permanently dictate the overall velocity of international commerce. The invisible mechanical synchronization across late-night sky corridors remains a testament to modern industrial transportation constraints. Human eyes looking from small passenger windows view only absolute dark voids, completely detached from complex structural navigation physics. Every single transatlantic journey forces advanced titanium and carbon fiber aircraft components to endure immense atmospheric pressure loads. Unlit maritime corridors hide the structural load limits where fluid dynamics parameters continuously challenge advanced thermodynamic structural design boundaries. This clinical investigation into oceanic tracking confirms why modern commercial transport operations purposefully obey raw environmental physics laws. The confidential files unsealed within our secret archives permanently prove that safety requires total mechanical and structural time discipline. Leave your empirical technical observations regarding atmospheric fluid mechanics below as we seal this transoceanic forensic case file. Planetary rotation dynamics combined with the Coriolis force generate intense high-altitude air currents resembling invisible rivers. Atmospheric stabilization at night minimizes vertical convection currents, allowing highly predictable cruise speed and precise arrival timeline calculations. Technical dossiers within our secret archives indicate that flight dispatchers must continually map changing upper wind directions manually. Titanium structural airframes experience deep temperature compression cycles while cutting across these dense sub-zero stratospheric boundary flight paths. Every individual mechanical component undergoes rigorous forensic evaluation to withstand the immense kinetic pressure of upper atmosphere drag. Ground-based technical controllers maintain absolute navigation safety limits without relying on continuous digital radar tracking systems. Flight crews actively monitor advanced physical analog instruments to verify precise position coordinates over the vast maritime void. Advanced meteorological specialists analyze daily upper air winds and thermal shifts to reconfigure the oceanic flight track grid system. Dynamic oceanic tracks shift miles northward or southward depending entirely on the physical movement of strong upper stratosphere currents. Flight crews pre-program these precise coordinates as fixed numerical nodes linked tightly to strict altitude and time parameters. Safe spatial separation inside these tight traffic corridors relies completely on minutes of separation rather than physical visibility distances. Any minor speed deviation quickly alters the strict horizontal buffer zones between closely packed, heavy commercial jet airliners. Even arriving 3 minutes ahead of calculations forces the traffic network to actively recalibrate safe operational parameters recursively. This rigid structure dictates why individual modern airliners sometimes decelerate intentionally to preserve critical time separation matrix intervals. Organized transoceanic track routing structures employ systematic alphabetical identification nomenclature codes to maintain cross-border operational consistency. These rigorous alphabetized designations remain entirely unnoticeable to sleeping passengers, yet form the baseline structural framework for transoceanic aviation. Even commercial passenger aircraft navigating outside the primary organized track grid must conform strictly to these overarching structural boundaries. Ascending directly into upper atmospheric layers requires airliners to cross critical thresholds between 9 and 12 kilometers altitude. At these immense vertical elevations, the cold, rarefied stratospheric air behaves drastically differently than atmospheric layers near Earth surfaces. The extreme kinetic behavior of uncompressed cold air masses manifests as a primary governing factor for transoceanic cruise performance. The unsealed technical logs within our secret archives document how high-altitude jet streams act like high-speed invisible rivers. These stratospheric rivers generated by global heat redistribution accelerate commercial airliners to ground speeds exceeding 1,100 kilometers per hour. Entering this powerful tailwave reduces overall travel time from North America to European destination hubs by 90 minutes continuously. Conversely, westbound return flights must battle intense opposing headwind forces, distributing their operational schedules across broader daytime flight windows. During daylight hours, solar radiation actively destabilizes the atmosphere, causing vertical air currents to disrupt precise velocity calculation metrics. Nocturnal cooling permanently dampens these turbulent vertical convective cells, ensuring high-precision timing across critical oceanic tracking checkpoints. Meticulous flight dispatchers constantly evaluate shifting upper air wind temperatures to modify the dynamic track boundaries every 24 hours. This hyper-organized network proves that transoceanic safety relies completely on the invisible structural architecture of the dark midnight sky. Beyond standard land-based communication networks, transoceanic airliners enter vast high-altitude silence zones, requiring high-frequency shortwave radio backup utilization. Inside this total sensory isolation, flight crews manage critical flight paths over deep, dark waters without visual references. If advanced digital power systems experience sudden, unexpected faults, mechanical analog gauges become the sole life-saving survival tool. Documents preserved inside our secret archives show that airframe resilience is tested against maximum structural distortion limits continuously. Cryogenic sub-zero temperatures threaten fluid distribution systems, forcing technical operators to monitor fuel freeze point thresholds extremely carefully. Invisible volcanic ash clouds hanging silently in the upper stratosphere can completely destroy titanium jet engine compressor components. This dangerous reality proves how a single unexpected thermodynamic breakdown transforms a smooth journey into sudden catastrophic failure. Severe structural pressure differentials exert massive compression loads against the outer aluminum alloys of advanced commercial transport fuselages. Rapid physical fractures propagate invisibly across pristine titanium composite wing seams under continuous high-frequency dynamic clear air turbulence vibrations. Any localized reduction in boundary layer airflow stability instantly terminates mechanical lift generation across the unblemished wing surfaces. Meticulous accident investigators within our secret archives cross-reference structural fatigue variables to prevent catastrophic in-flight decompression disasters. Two technical flight operations dispatchers evaluate printed paper charts to divert airliners away from dangerous horizontal wind shear bands. Extreme high-velocity atmospheric streams generate massive kinetic resistance, demanding absolute precision during high-altitude speed adjustment phases. Mechanical needle indicators fluctuate sharply on physical cockpit gauge instruments, documenting real-time changes inside the sub-zero stratospheric layer. High-altitude operations demand absolute structural integrity, as commercial airliners traverse highly unpredictable upper atmospheric pressure vector transitions. Experienced flight crews manually verify physical log data on printed charts when sudden solar radiation fields cause navigation errors. The unsealed technical files within our secret archives document how extreme cryogenic temperatures alter advanced aircraft structural composite behaviors. Turbine propulsion units must withstand severe microparticle abrasion when passing through invisible high-altitude volcanic dust suspension fields. Sudden vertical draft currents exert immense mechanical moments across titanium wing spars, risking instant catastrophic aerodynamic lift disruption. Ground-based dispatch personnel manually coordinate alternative routing parameters to maintain safe vertical spacing margins during global emergencies. Total containment shell fractures remain an implicit threat whenever raw thermodynamic variables exceed calculated safe structural design threshold limits. Mechanical resonance testing reveals how rapid velocity changes impact the titanium structural joints of transoceanic passenger jet airframes. Flight crews actively reduce engine throttle settings when encountering high-density turbulence pockets to protect critical wing spar joints. Specialized meteorological data logs preserved within our secret archives prove that stratospheric shear layers shift locations constantly overnight. Ground tracking personnel manually analyze raw pressure readings on paper charts to establish updated vertical separation corridor boundaries. Extreme thermal contraction cycles manifest across complex composite carbon fiber panel seams during prolonged sub-zero oceanic transit phases. Highly pressurized passenger cabins rely completely on continuous mechanical seal integrity to isolate occupants from stratospheric vacuum conditions. Mechanical analog clocks rhythmically tick inside dark flight decks, confirming precise chronological milestone tracking over the starless ocean. The structural stability maintained within these high-altitude corridors prevents cascading delay vectors throughout tightly integrated international transportation networks. Saving multiple tons of unburned liquid kerosene directly optimizes global aviation supply logistics chains across multi-layered distribution hubs. Any microscopic mechanical failure caused by extreme thermodynamic pressure changes threatens the immediate containment parameters of advanced propulsion systems. Structural engineers cross-reference empirical load data logs preserved within our secret archives to eliminate catastrophic material fatigue vulnerabilities. Regional traffic coordinators modify tracking intervals manually to maintain standard lateral separation buffers over vast unmonitored maritime voids. Flight crews actively regulate precise aerodynamic velocity settings to match volatile clear air turbulence variables inside the upper stratosphere. Absolute chronological discipline enforced through physical timekeeping instruments guarantees survival when crossing these isolated high-altitude blind zones. Advanced commercial passenger airliners maintain steady linear trajectories across cold stratospheric boundaries during high-altitude midnight cruise phases. Massive composite wing surfaces experience continuous aerodynamic torque stress, requiring flawless mechanical resistance properties from titanium alloys. Physical analog instrument needles vibrate instantly to document sudden localized air pressure drop anomalies inside the sub-zero stratosphere. Rigid flight crews actively maintain total spatial control, utilizing manual analog flight controllers through deep sensory isolation windows. Ground operations teams analyze raw technical telemetry blueprints manually on heavy slate tables to enforce absolute systemic safety. Uncompromised turbine propulsion units continually process thin atmospheric airflows to balance structural thermal contraction constraints overnight. The verified intelligence inside our secret archives highlights why total mechanical discipline eliminates implicit catastrophe over dark ocean voids. The final downward descent phase through dense maritime cloud layers demands absolute compliance with fixed numerical mechanical trajectory vectors. Taxiing smoothly onto the clean, unblemished concrete apron seals the mechanical operational loop of this complex transoceanic flight vector. Inside the quiet flight deck, exactly 2 uniform pilots execute the final physical shutdown protocols using heavy analog switch configurations. Forensic investigators manually insert the printed paper data log sheet into a heavy, pristine titanium storage container for protection. Subscribing to our secret archives ensures immediate access to verified technical dossiers documenting hidden risks across global transport networks.